Hey guys, how are you guys doing on this beautiful Saturday night? I'm doing well filming physics videos. Here is problem 8b of Bensky's Gauss's law problems that he gave us on that handout. You can probably find them on Polylearn as well. This problem is asking about infinite planes, or an infinite slab, that and the E field around it. So let me just read the question here. It says a rectangular non-conducting slab is infinite in the x and z directions and extends between plus and minus y naught along the y-axis. It has a constant charge density of rho. And question B asks to use Gauss's law to find the electric field at a distance y from the center of the slab, where y is greater than y naught. So this part right here is the part we're focusing on. We need to know that the area that we're the location that we're interested in to find the electric field at is outside of the volume of the slab, so it's beyond the slab. So we can kind of draw an image. It'll be something like this. Go ahead and draw our slab in here. And the slab has some depth and extends. You can kind of imagine that it's going to extend in this direction and this direction to infinity. That does something special for us later. Makes it so we are not worried about the charge passing through at an angle. All the charge is directed, or all of the electric field is pointing away from the slab. So this depth here is, since we stated that it extends between plus and minus y naught, we know that this depth here is 2 times y naught, and that'll be useful for us. We know that the point that we're interested in finding the E field at is somewhere beyond the slab, so it's not within the slab. Problem A is worrying about the same question, but the area that you're interested in is inside of the slab. So that adds different parameters for this problem. Obviously, this is going to be a Gauss's law problem. It tells us right off the bat. So one thing we need to know is that the closed integral of E ds equals our Q of the closed surface over E naught. We know our E constant, so that's going to be easy for us. The difficulty parts with this are on the left side, integrating the area of ds, which is pretty much the area of the shape that we use to find the charge, and finding Q, which is the total charge within that volume. So we can start right off the bat by pulling E out of the equation. Well, I guess first that we need to choose what kind of Gaussian surface we want to use. You can either use a cylindrical Gaussian surface, or you can use a cubic or rectangular Gaussian surface. In this one, you can't encapture all of the slab because it stretches to infinity in both directions. So you won't be able to encapture all of it. So what you're going to do is you're going to take a sample of this area, and you know that on the sides of the slab, none of the E field will be pointing in the x or z direction, and that's because it's all like we said before, all of the electric field is directed upwards. So what we'll do is we'll use a cylinder, just as easily could use a cube, but it doesn't matter. I feel more comfortable with cylinders for some reason. And so we're going to imagine that's our cylinder right there. And we know that it'll be reaching up to some height, y. And same, it'll reach down to this height, y, or negative y, I suppose. And now we want to calculate the Gaussian surface interacting with the charge. Now we notice that in our slab, all of our charge is being directed in the vertical direction. So it's going to be going right up towards right in the y direction. So you can imagine on our cylinder, we have these surfaces, and our charge is passing up. So when it hits the surface, the charge at that surface is going to be on the faces of the cylinder will be up, and there will be infinite number of those guys in there, and also down here, down and down, and then in here there'll be parallel to the surface, so they won't actually interact with that surface at all. So we don't need to worry about this length. So we know that the surface area of a cylinder we can just write as 2 pi r squared times height. Oh, times height times the circumference of one of the circles. So that's kind of if you unroll it into 2 circles and 1 rectangle, then you get height times 2 pi r, which is your cylinder, surface area of your cylinder. We know that we can knock out this guy because that's going to be 0 because they're all interacting. They're all going against the flow of the surface. Now that we have that, we can move on with our left-hand side of our Gaussian equation. So let's start to look at individual parts of the Gaussian equation. So the closed integral from E ds, this is the left-hand side. What we're doing now is we're going to have constant electric field at both of these faces. So we can do something, and that is to pull out the E value and just take the integral of closed integral of ds. And ds is the surface area that's interacting with the electric field. So that is 2 pi r squared. So that's going to be our oh, and that's times E because we pulled E out. That's going to be our left-hand side. So we'll keep that in mind. And now we'll go over here to our right-hand side. Right-hand side. And our right-hand side will be the charge in the closed volume divided by our constant E. So our charge is going to be the same as our charge density, rho. Or well, here, let's write this out first of all, is QE over E naught. Yeah, so now we're going to do rho times volume divided by E naught. Now, to get this volume, what we're going to be doing is we're going to be integrating across the whole entire shape. So this is where it gets kind of tricky. We have a constant density, so that kind of saves us a little bit of work because we don't have to actually integrate a density equation. But to just find the volume, we can either do this logically by knowing what the volume of a cylinder is, which is just the area of the base times the height of the cylinder, or we can do it by integration. I'm going to show you integration because that's a little bit trickier, and that's probably how you're going to need to know how to do it if we have a variable rho here. So if that guy gets variable, or is variable in the problem, you're going to have to use integration to solve this. So first what we're going to do is we're going to pull out 1 over E naught, so we don't have to worry about that. Then we're just dealing with the triple integral of rho, and that's going to give us rho inside, or rho times the volume. So we go rho, and then we do this funky thing at the end when we're going to be integrating with respect to theta and a radius. So we do these values times r, dr, dy, d theta. It's good practice to always put d theta at the very end, especially when you know you're going to be going from 0 to 2 pi. That helps out a little bit. This constant r is one that you're going to have to remember. Just so happens that when you start moving away from the plane, you have to multiply by, away from the origin, you have to multiply by this constant r to compensate for a little bit of change with r with respect to d theta. It just kind of changes a little bit, but you can just memorize that. The next thing we're doing, we're integrating with respect to dy, and that's from our height negative y all the way up to y. As you can remember from this guy, negative y is down here, or over here, negative y is down here, and then positive y is up here, so we're going to integrate along that whole distance. And then on the very inside, we're going to be integrating with respect to the r value. So we can just go from 0, which is the center of the circle, up to r. It's the radius of our cylinder. So this is the most basic version of our integral. We know that this is a constant, that's why we're allowed to have this outside. Also, in this equation, we know that rho is constant, so we're going to go ahead and pull rho out. So we're going to do rho over E naught times this integral. Now this integral is going to simplify down quite a bit just to give us the volume of a cylinder. You can work it out, but more or less what happens is the function is it's only a function of r, so only when you're integrating with respect to r over here is this function going to actually change, so it's just going to become squared at that point. Once you work all this out, you get out your 2y naught, or 2y times rho times pi r squared. That's our right hand side. Now what we're going to do is we're going to combine them two and see if any magic happens where we can cancel out one or the other, or cancel out things from either side. So we'll do 2 pi r. Make sure you guys can see this. Sorry. Oh, you also missed a little bit of my last work. You can catch up on that. You can pause the video if you need to catch up. Pretty much all we were doing here is writing out the integral and then integrating. The only time that we are multiplying by anything but a constant is when we're integrating with respect to dr, and that's because there's an r value in here, so you're going to get an r squared out of that, and that shows right down here. Alright, now writing our equations together is 2 pi r squared times e equals rho over e naught times 2y times oh no, we already multiplied by our rho, so you can scratch these guys out. I'm sorry for that. That's a little bit misleading. I pulled out rho at the very beginning, so we don't have to multiply by that on the inside again. Times pi r squared. Now we can cancel a couple things out. We have 2's on either side. We have r squared on either side, so we see as kind of logic tells us that it doesn't matter the radius of the cylinder that we choose to multiply by. And we have pi on either side. So that shows that even with, like, similarly to a cube, it's not dependent on pi, so we could have used a cube equally. And now we have E equals 1, so this is our electric field, equals 1 over E naught times rho y naught. And that's the simplest equation that we can really get out of this, and we see that it's dependent on how thick the slab is here, the density of the charge within the slab, and those two things will determine the electric field felt distance y away from the slab. Yeah, that's more or less it. I can show you guys the whole page again one more time, so if you want to check out any of the work, pause the video at any time, please feel free. This is the work that I went through. Again, this is doing the left and right hand side separately and then joining them back in together here. I think it's important to split them apart while you're working on them so you don't confuse yourself trying to do two things at once. I hope this helped, and enjoy your week. Good luck on your midterms, guys.